So thank you so much, Professor Sun, and thank you for the invitation. And it's wonderful to be with you all here, in my basement. Wish I was there with you in person. I look forward to future ICRAs where we can all be together. So I'm going to share here. So as Professor Sun said, I'm going to be talking primarily today about some of our efforts in soft robotics, in particular in leveraging some of the past work over the past, let's say, decade or so on the development of soft material actuators and devices towards dexterous and delicate manipulation tasks. But first, the last time I spoke with you was in ICRA 2013, and this was a talk that I gave there that was a plenary on the Robotics project. So this was a project that is trying to create flying robotic insects. And we've had, I figured maybe it's appropriate just to give you a couple of brief updates on progress on that topic since last time we spoke. I'm not going to go into all of these details, but a number of flight control demonstrations, advances in various actuation technologies, various demonstrations of these devices doing things like aquatic and aerial hybrid locomotion or perching and unperching from various surfaces. Various architectures we've looked at, 2-wing and 4-wing, and a couple of nice firsts, in particular development of soft actuator powered devices, as well as some of the first demonstrations of power autonomous flight. But I'm not going to talk about any of that. I'll give you maybe a couple of brief highlights. This was a paper that was by Moritz Grau, who developed some electroadhesive based perching mechanisms and allowed the Robotics then to sort of land on and take off from a variety of surfaces, both natural and synthetic. And I won't sort of play this whole thing. And another one more recently, we had a big effort to push for power autonomous flight. So this was a demonstration that happened a couple of years ago where we took our device, which consists of these piezoelectric bending biomorph actuators, flapping wings. We developed some onboard signal generation and drive and power electronics that boost a low voltage to a high voltage and then sort of distribute that voltage to the plates of our piezoelectric actuator. And then of course we've got solar panels on the top here, and this led to the first demonstration of untethered flight. So this is solar powered. This is you see a tether here, but it's just tethered just for safety for the vehicle itself. And so this is something we were very excited about. This is slowed down. This was recently the cover of Nature. This was a couple of years ago now. And I'll just give a plug to Noah Jaffrus and Farrell Helbling, who are now at UMass Lowell and Cornell, respectively, for leading that work. But that's not what I want to talk about today. Okay, so there's a bunch of stuff I could go on and on about some of the stuff at small scale robotics, and if we have time, I can come back to a couple more things. But really, what I want to get to is some of our recent passion in trying to leverage this big push in this. I don't even know if I can call it a nascent field of soft robotics anymore. To leverage the promise of some of these soft systems towards delicate and dexterous manipulation. The delicate side is now straightforward, and that's been demonstrated over and over again, and I will show some of that. It's really the dexterous part that I want to get at. How can we get towards things like human level dexterity? And this is a video courtesy of our friend Oliver Brock with Julia Childs, showing a rather complex manipulation task of a potato and doing chopping, all sorts of reorienting. All sorts of constraints built in here, and a lot of obviously perception and planning on the part of the human. So how can we get towards human level dexterity like this? And the classic approach, and I'll give a few examples of this approach in a few slides, is to really understand the system. So have a lot of perception, model interactions, have a very good internal model of your manipulator, and then rely on control, both local and global control, to do the planning and the execution of these motions. And what I'm going to propose is that we change this a bit and use compliance to both limit the forces that we can apply on things. So this is what I was alluding to before. We're inherently delicate, so that's not a problem. But also to accommodate for things like errors that we would have in positioning and planning and any sort of disturbance that might happen. And our friend Ken Goldberg put it very, very nicely in his recent piece at the beginning of a Science Robotics special issue on grasping and manipulation, where he described the consequences for even small errors in placements on a manipulation task, on a grasping task, and it's true. And compliance, I would propose, can get you some of the way there towards overcoming some of those errors. this is another interesting in-hand manipulation task by a local drummer that I contracted for this video. But this is, again, human level dexterity tasks, and I'll also mention several times things like in-hand manipulation. So what can we do? How can we reorient an object that we have in our stable grasp? And how can we move it around with various motion primitives? And I'm using that sort of as a proxy for a really challenging task for robotics, and something that humans do very well. So again, this field is, again, as Professor Goldberg points out, this is like a 70-year problem. People have been thinking about robotic end effectors for about that long. And I'm not going to give, it would be several talks long just going through the history of this, but I just wanted to give a couple which sort of illustrate, which I've sort of cherry-picked to illustrate my points here. So in the past, achieving human level dexterity, and some of these are current efforts, has focused on a lot of bioinspiration and perhaps even towards the point of biomimicry, and for these mostly anthropomorphic hands that I'm showing here. And that leads to a lot of degrees of freedom, a lot of articulation, a lot of actuation. Those actuators then tend to be located more away from the hand itself, more sort of proximal to the arm, if you will. But all of these tend to have the same sort of characteristics. There are many degrees of freedom and challenges then for control, for performing some of these dexterous manipulation tasks. So one way to sort of avoid this, when you have systems like this which are basically intractable, to come up with full models that capture not just all of the sort of internal motion and dynamics of the hand, but also interactions with objects, in particular with objects that may have unknown properties or compliances or various things that might trick perception systems, etc. So these things become fairly intractable to model. So one wonderful technique that is opening up is the use of some machine learning techniques to try to train some of these motions, classify motions, motion primitives, in this case for in-hand manipulation. And so this is one perhaps successful path towards achieving this level of dexterity. Well, I'm not going to describe those sorts of techniques. That's not my area. I'm a hardware guy. And so what I want to do is I want to make some of these problems easier. I want to make some of these problems easier by strategic compliance that are going to, again, overcome these sort of issues with positioning errors and precise contact locations, and while simultaneously minimizing the consequences of those errors. Those errors are going to happen no matter what, but can we minimize the consequences of those errors by virtue of the compliance of our devices? But that brings up a number of questions. So we can make things out of soft materials, no problem, and I'll tell you a little bit about that. What do I give up there? I mean, I give up some precision, perhaps. Do I give up some degrees of freedom, perhaps? But I give up perhaps some strength as well. So I want to talk a little bit about soft yet strong. How do I reconcile dimensionality? I already showed you a few examples which have 20 odd degrees of freedom, not counting the sort of rigid body degrees of freedom of the things that I'm manipulating. So how do I reconcile this dimensionality? Now I'm pushing that further. Now I'm taking something which are basically continuum manipulators, and how do I think about that? And when should I take inspiration from what humans do, both in terms of our hand structures as well as some of insights that are being developed for grasp and manipulation strategies? But first I wanted to talk a little bit about some of the history of soft robotics to frame us. Despite the recent, and I'll say recent being the last, say, decade or so, sort of uprising and popularity of the topic, this is not a new topic. I would go back to the late 80s when Professor Suzumori has developed some of the first, that's in the upper right, and I encourage you to go try to find some of the videos that they had from the late 80s. They're fantastic. And they were doing some of these fluidic actuation systems based on elastomers back then. They were doing some really interesting things, some manipulators, some little locomotion devices, etc. I remember back when I was a grad student being inspired by some of the work of Ian Walker, developing some of the first continuum manipulators that were modeled after elephant trunks. Then around the early 2010s, and this is not exhaustive, of course, so I apologize if I'm missing your favorite example here. But around the 2010s, there was a renewed interest in this area And this was spurred perhaps a little bit by, there was a DARPA project at the time called ChemBots, chemical robots, that pushed a number of these technologies, from jamming grippers, some of the stuff that George Whitesides was doing that eventually turned into a company, Soft Robotics Inc. And then, of course, the popular press and media got interested, and these things started to appear in movies. For example, Baymax, I'm sure that we're all familiar with. Launch of various toolkits that exploit the accessibility, the native accessibility of some of the techniques used in soft robotics. The journal Soft Robotics, which prior to a couple years ago was the highest impact factor journal in all of robotics prior to Science Robotics taking it over. And then a number of other firsts in terms of fully autonomous robots, if you will, and robotic fabrics, starting to really recognize the sort of human-centric opportunities that arise from soft robotics through the wonderful work of Rebecca Kramer at Yale and Connor Walsh and other people that are working in more sort of wearable type robotics. So now focusing back on the task at hand, which is manipulation, I just wanted to give a couple of plugs to what I see are some of the really the examples that stand out in inserting compliance into grippers, into manipulation systems strategically for the reasons that I had already sort of motivated. And the first that comes to mind is the hand that was developed by Aaron Dollar and Rob Howe at Harvard, and now Aaron's at Yale. That was based on this really nice technique of shape deposition manufacturing, where I can sort of get free-form three-dimensional components with either rigidity or compliance or other components placed strategically throughout the device. And they did this sort of fantastic set of examples where they could be extremely robust to different environmental and different object constraints, sizes, shapes, compliances, and really just beat this thing up in ways that you would never want to do with a more sort of traditional, rigid, brittle type of manipulator. And they had some fantastic demonstrations with this, and this is something that goes on to date both at Harvard and Yale. Similarly, the work of Mark Kokoski and colleagues and Dan Alkes, who used to be at Harvard and is now at Arizona State, had some similar type of architectures, again building up from this shape deposition manufacturing process. And I'm showing this also because there's some foreshadowing here. These were applied to the wonderful device Ocean One by Osama Khatib, Mark Kokoski and colleagues for ocean exploration. So keep that in mind. I'll come back to some of our work in this area in a minute. What about sensing, you might ask? So there's been also a number of really exemplary methods that have been demonstrated for taking these now soft manipulators, soft digits, and embedding, in this case, resistive sensors based upon conductive liquids. And so this was a demonstration where they used this technique. This is with Jennifer Lewis at Harvard, where they used her technique of embedded 3D printing to simultaneously create the shape, but also the internal vasculature, which houses some of these conductive liquids that perform sensing tasks, and showed that they can be very robust to various conditions by feedback using these tasks. There's carrying on with this theme, there's wonderful work out of Rob Shepard's lab by Weichen Zhao, who's now at Tsinghua, on optically innervated sensors within soft hands that allow object classification and tasks like that. And then there's the absolutely brilliant work out of Oliver Brock's group that is looking into creating acoustic sensors. So basically having a microphone and a acoustic source that are internal to the soft material structures of the digits here, that then can determine the location and magnitude of contact through some machine learning techniques. And as a good segue, Oliver's group is also involved in a number of really fantastic, they're the leaders in this area of soft, dexterous, delicate manipulation, in particular for things like in-hand manipulation. So the ability to sort of manipulate objects within a grasp. Again, using manipulators that are so soft, using end effectors that are so soft that there's no chance of harming these objects as well. Okay, so with that overview, and again, apologies that it's not exhaustive, but I want to get into some of the things how did we get involved in this? And so our involvement in this area started when I saw this video. And I saw this video, this is at a National Geographic conference that I met my now colleague David Gruber, And he was showing videos of the state of the art at the time. This is from NOAA, where they were trying to do deep ocean sampling of various organisms. And you can see from the previous video that if they do get something in their grasp with this sort of jaws of life looking end effector in this way overpowered manipulator that's meant for the oil and gas industry, then they're just going to mangle whatever they touch. Or in this case of this echinoderm, which is surprisingly fast, they're not quick enough to get it. And here's another example of something which is makes me sort of cringe looking at this. If I want to sample this organism, get it up to the surface, I want to do that. I want to do so intact, right? I don't want to be mangling this thing where it's going to start to give various gene expressions which are not true to its sort of actual nature in vivo. And so I want to get around this. I want to be able to. This was I saw this, okay, and I said, well, okay, well, we can do better than this. And right about that time, this was about 2013. And this was with work with Kevin Galloway, who's now at Vanderbilt. He was starting to make these soft digits and making these in ways that were pretty simple. He's just taking these elastomeric bladders that are shown in these videos and these diagrams on the left. And these bladders are just very simple. They're just elastomeric balloons. If I inflate them, they inflate just as a balloon would. But if I start to then put inextensible materials, whether they be sort of sheets of various fibrous materials or fibers themselves, Kevlar fibers woven into the structure of this thing, then based upon where I put those fibers, those reinforcements, those inextensible materials, then I can guide motion. I can do this entirely passively, of course. There's no sensing in any of these things. It's just guided by the pressurization and how these inextensible elements are arranged such that I get, for example, extension bending twist coupling or extension twisting coupling, again, just based upon how I arrange these fibers. And so that's a nice way to pre-program motion. We started to realize this almost a decade ago now. So based upon those videos and that we saw from NOAA and those motivations for deep ocean sampling and some of the things that we knew that we could do, we started to work, myself and David Gruber and Brendan Phillips, who's now at the University of Rhode Island, got together and created these soft manipulation systems, attached them to end effectors on remotely operated vehicles that you're seeing here. Went and did some diving in the Red Sea off the coast of Eilat in Israel. This is a shameless plug to our sponsor. But you can see this little pink digit here, which is sort of coiling around this little flag. And so, what is this thing? So this is a soft gripper, okay, which is now focused specifically for long, sort of high aspect ratio, wispy kind of corals. And so the goal of this expedition was to demonstrate these technologies, but also to do deep ocean sampling beyond the depth where technical divers could get. So that there's no hope of humans actually manipulating these things. It has to be done by robots. And so how can we do that? And you can imagine that if I'm on a boat, this was only a couple hundred meters deep, but I'll show you videos in a minute where we're a couple kilometers deep. You can imagine doing that just teleoperated, the ROVs moving around, the boats moving around. I only have 2D vision, good cameras, but I only have 2D vision. And now I can imagine with a more traditional gripper trying to go down and do a pinch grasp with this thing, it's hopeless. And so this one is just an extension twisting coupling elastomeric actuator, which just upon pressurization coils up. So I can just get close enough, pressurize it curls up and stably grasps this object. We can also do things more sort of anthropomorphic as well. This is the first demonstration of grabbing this sort of broccoli-looking like coral structure, giving it a gentle hug, and then sort of pulling it from the ocean floor and sampling. So this was the first successful sampling. We also then got on board the Nautilus, which is Bob Ballard's boat, a more capable boat, larger, bigger ROVs, and started to go even deeper. This is off the coast of California now, where Kate Becker, who her name will come up a couple times, she's going to be starting at MIT next year, was developing some of these soft fingers, derivatives of the ones that I just showed you, but now more going to greater depths, a number of other features to limit the sort of stresses that are incumbent upon the animals. And so we're able to, just fast forward this, but we're able to now grab onto these echinoderms, these holothuria at the bottom of the ocean. And these things are extremely delicate, but nonetheless we can sort of pick them up, put them down. That really demonstrates some stable and effective grasping techniques. We can do this with rigid animals as well. This is a crab. Sorry for that. chatter there. We can do this with sort of delicate but not soft. So this is a crab that's being sort of gently hugged, picked up, and then put back down. And we can do it with all sorts of other things too, like sea stars and mollusks, etc. So so we can bring these things down to the bottom of the ocean and grab stuff based upon all the rest of that apparatus was a rigid end effect, was a rigid manipulator that was basically just holding a soft end effector. We also did some expeditions in man submersibles off the coast of Brazil, where this is now, you can kind of get a glimpse here in the next video, you can see it a little bit better, that are now the entire, and not just the end effector, but the entire manipulator, or at least up to the elbow or so, is soft in case, one of the things that we saw is that we were, even though the hand was soft, we were bumping into various structures at the bottom of the ocean. We were trying to do these sampling tasks with the rest of the manipulator. So this is a motivation to make the entire thing soft, and this is grabbing a pyrosome. Other interesting thing here, you can't quite tell, but this is Brennan. He's wearing this little glove that has some sensors in it, which are measuring his motions and then converting that into the motion of the end effector in the arm. This is not soft, so what I'm about to show you is not soft, but I think it's really cool, and we're about to do another expedition on another version of this, so I thought I'd give this as a preview. But the sort of themes are similar, and the themes specifically are, we want to be respectful of the marine life that we encounter in the deep ocean. Some of this life, by the way, is thousands of years old, very slow growing, very slow moving. So we want to be respectful of that. Some of the animals we might not even want to touch if we want to sample them, or maybe we want to capture, study them, and let go. And so this was a study with the Monterey Bay Aquarium and Research Institute off the coast of California, where we created this sort of folding mechanism. You'll see it here in a second. Now this is in the midwater. This is not sort of stuck to the bottom of the ocean, and it's grabbing this cephalopod and totally unharmed, probably a little annoyed with us, but totally unharmed, and then can release. So there's no sensing or anything happening here. The next generation is going to be more capable in terms of, well, what else can we do? We put vision systems in here. Can we measure, kinematics or morphometrics? Can we put some chemical sensors in there for respiration? Perhaps even do some, delicate biopsies for sampling for further sequencing. All right. Anyways, so now we're at the point where we've got our interest up, and we said, all right, well, we can do all these things. We can put these things at the bottom of the ocean, and they work really well. The materials, I didn't show you all the sort of background here, but we can pretty quickly produce these digits. They're basically indestructible, and even if they do spring a leak, we can just sort of pop one off and replace it without much problem. So now we want to get back to these sort of main questions of the talk, which is, the first one is, now, what are we giving up when we go to these soft elastomeric materials, and what can we do about it? And so one of the things we give up perhaps is strength. So if I've got something which has modulus on the order of 100 kilopascal, how can I hope to grab huge things with large payloads? And so this is work with Shuguang Li and Daniela Roos at MIT, who developed these really, Shuguang developed this really cool concept of this. He calls it foam, fluidic origami artificial muscles, where you've got this sort of blue, and here is this sort of folded structure. You wrap basically a bag around it, and then suck a vacuum on it. And now as the vacuum pulls the air out, the membrane here sort of provides the primary force, both the pressure differential and the tension in the membrane pull on this internal origami skeleton, and then by virtue of how the skeleton is arranged, that skeleton then guides the motion of the internal structure. And so you get, again, this sort of motion programming that you got from our previous examples of these inextensible materials. And you got this fluidic actuator. This has a number of interesting characteristics for it. I don't have really time to get into. I just want to highlight a couple. One is that you can sort of design this internal structure however you want. So you can be a simple linear actuator, or it can be more complicated motions that are guided again by how the fold pattern of this device is. So we can think about just sort of general motion, picking things up, or we can think about having guided motion that might be for gripping a particular object shape. And so here's an example of the former, where I just have a relatively simple device that is picking up this car tire. And this is, let me fast forward here. Okay, so to pick this thing up, Now, one thing to note is that if I think about what are the metrics I might care about here, I might care about this sort of payload that I can pick up, sure, but I also care about the payload relative to my arm mass. And so for this case, I'm picking up something that's about 20 kilograms, and I've got roughly a 2 kilogram total arm mass here. And this is cheating a bit, right? Because I'm not talking about the fluidic engine that's driving this or the control system. I'm just talking about the manipulator here. So with that caveat, whereas more sort of common commercial manipulators have this, whereas the ratio of payload to weight for this device might be on the order of 10, we're getting several orders of magnitude greater than a commercial payload. But again, what are we giving up here, and what's the differences here? I'm not talking about precision yet, okay? And then more on the sort of on the grasping side, again, Xi'an realized that I can not only sort of create these linear actuators with these kind of mechanisms, I can do a bunch of other things. I can create structures which deform in ways which are useful to grasping, in particular grasping in the presence of uncertainty. And so he did a study using this magic ball folded Muri origami mechanism as the internal skeleton for a number of household objects. And this is the subject of a paper he had a couple years ago. So that's soft and strong, and it's getting a little bit into the grasping realm, soft grasping realm. And one of the things that's maybe understated about what I just said was that super delicate. None of those objects were harmed, and so you can really sort of capture the promise and the benefits of these soft approaches. But what about dexterity? So that's what we wanted to get to, and this is something that we've been focusing on in my lab now for quite some time here, where we want to go from this sort of simple demonstrations where we had on the left to something more complicated, something that can not necessarily do everything that some of those initial rigid high degree of freedom manipulators had done in the past, but again, exploiting, making connections is what we really want to do, from advances in soft condensed matter physics and mechanics and behaviors of various materials and metamaterials. Link that with some of what robotics has been doing for the past 20, 30 years in terms of hand designs, and see if we can get some of the best of all of these worlds. And that's where we want to get to. And so for that, I'm going to talk about 4 or 5 different subjects. I'm going to try to go through these brief and give plugs where I can, so that you can see. There's another talk at ICRA from one of my students, Clark Teeple, who will go into some of this in more detail. But I'm going to talk about a few things. Digit design. So how do I design an individual finger? I think about that, and that's in hand design, and then maybe even a little bit of tribology on the surface. How do I modulate the surface friction? So these, I'm not going to claim that this is going to be everything that you could possibly do with design of these soft hands. This is really just the tip of the iceberg, but we had to start somewhere, and this is where we started. I'm going to jump right in. So the first thing that we did was explore, taking those grippers that I showed you before, which are composed of individual digits, which just have a single degree of freedom. I inflate them and they bend, and that's it. And we can do all sorts of things, and we have done all sorts of things with respect to characterizing that motion, modeling that motion, adding various things onto the surfaces to further limit stresses on objects that you encounter, etc. But now we want to get into, again, with a motivation of things like in-hand manipulation, things like what we can do on a human level dexterity. What can we do to increase the dexterity or increase the degrees of freedom of a given digit? And so the first thing that we explored was having parallel degrees of freedom, where we basically just split the actuator down the middle, and now in addition to bending, I can sort of get this side-to-side motion. It's conceptually straightforward, but allows us to do these. Now to start to do some of these motion primitives. We start to program in motion primitives for in-hand manipulation. So things like translations in 2 dimensions or rotational gates. And so if I wanted to, again, reorient this object in my hand here, now I've got some tools to allow us to start to do that. And we can do all sorts of things, reorienting object, unscrewing caps on things. And this is work of Clark Teeple, who again he will give a talk not on this subject, I don't think, although I'm sure he'll show highlights at this ICRA. This is another thing that this allows us to do is think about. Now I know the state of my end effector, then I can start to use some of these additional degrees of freedom, not just to control motion for these motion primitives, but I can also start to compensate for gravity, which might be a trivial thing for something which is rigid and not back drivable, but for some of these soft systems, I do have to worry about this. Moving on, another exploration that we've done with respect to digits is serial degrees of freedom. So this is another fairly sort of obvious question would be, well, if I can sort of split my individual digit into 2 halves and actuate them both independently, then what do I gain from that? And the answer I'll jump to is that, well, I gain both sort of power grasps and pinch grasps just by choosing which of these segments I actuate. But there's a question in there of, okay, well, how do I design the system? And just thinking about a simple parameter like the ratio of those two link lengths. So one thing I could do is I could go through a sort of experimental process where I build these things. That gets a little bit trickier, a little bit tricky, despite what I'll tell you in a little bit about how we can manufacture these things pretty readily in our lab. Still, it's a pretty heavy lift. And so what we've done, I'll just give a preview, I'll come back to this in a few slides. Moritz Graul has developed this architecture called SOMO. It's a soft robotics simulation environment based upon PyBullet that allows us to do simulations, and we can also calibrate these the sort of actual end effector properties, the continuum manipulator properties, to real life experiments, and then run these sorts of grasping experiments, asking questions about what is a more effective grasp as a function of different parameters, in this case the distal segment ratio. And so this allows us to sort of rapidly speed through a variety of tests on various parameters. Again, this is just on one parameter, much faster than we can do with experiments. And then that informs our designs. We implement those designs and further characterize. But just to give a plug, this is something that's under review now, hopefully you'll see soon, but just to give a plug for this environment, the SOMO environment, we can do things in hours that would take us, better part of a day or longer, with much higher resolution and fidelity and the types of things that we can simulate. And very good physics. I'll show you some examples in a few slides, but we're capturing the dynamics of these systems rather well. So coming back to this sort of multiple degrees of freedom, serial degrees of freedom, you can imagine I'm not showing the ability to do a power grasp on large objects with this kind of architecture. That's straightforward. One thing that we started to realize that is perhaps unique about these things is the ability to do pinch grasps on arbitrarily thin objects. This is picking up a piece of fabric. And so this is nice. This shows that by selection of which of these segments we're actuating, we can then pick up very thin objects, do simple things like folding tasks. This one in particular might be reasonable to do with a rigid system, but the one where I'm sort of pinching and pushing into a table, I better have really good perception and understanding of my reaction forces to really understand what's happening there. Otherwise, I might damage my otherwise rigid manipulator. In this case, no problem. And Clark also did a demonstration here. This is partially motivated by a NASA project that I'll allude to later, but where we can use these things to also sort of, again, manipulate thin objects, apply tape to surfaces, for example, in addition to some of the folding tasks that I showed you before. Another topic that we might, okay, so that's in the digits themselves. Now, what about how I arrange these digits and the design of the hand itself? Okay, so one of the things that we recognized a few years ago and have been working on since is that, well, okay, the palm structure in your hand can be just a passive surface by which I can sort of, think about having reaction forces or thinking about, gravity compensation, whatever. But what if I could make that an active part of the grasp? For specifically the challenge here is if I think about having different sized objects, and if I have different sized objects, they might interact with my fingers at different locations. Ideally, perhaps I want to manipulate these things either with a portion of the fingers where I can do a pinch grasp, okay, and that would give you the maximum manipulability. And if I have just sort of in this very simple example here, if I have something, if I replace this line with something that is a different size or different shape, then I might not get that with the same palm design. And so one of the things that Clark and Grace and others in the lab have done is think about, well, how can we understand a design of an active palm? In this case, is a rigid palm that's telescopic, that can interact with objects of various sizes and sort of push them into more ideal locations within the grasp. And again, we can go to our simulation environment and leverage different objects, for example, in the YCB object set, and ask questions for different palm sizes and heights and shapes and widths. How does the presence or absence of the palm affect our ability to do some of these various motion primitives for in-hand manipulation? And you can get it for this video gives a very simple demonstration. If the palm is inappropriately sized, as in the left, where it's in this case too large, then I can't, it's interfering with the motion of the digits themselves. So that's it's sort of conceptually straightforward, but we can do a more rigorous examination of this for various objects, looking again in our simulation environment, but also some experiments here. And again, Clark will go into this in a little bit more detail in his talk, so I encourage you to check that out. I wish I remembered when it was, but it's sometime this week. And we can look at things like manipulation success rate as a function of various object sizes and palm diameters and whatever other relevant parameters are. Start to construct active palm devices using this is just using a single actuator that is just sort of raising or lowering the center of the palm as appropriate, and then integrating this within our soft digit structures. So that's palms. And we've shown, using this architecture that we can grasp then and do some of these motion primitives around objects of various sizes and shapes. But it doesn't really end there. It's also quite useful for not just, you notice in all those other examples we're using gravity basically to support the object on the palm. But we can do this in free space as well. Again, just using the palm as a surface by which I can sort of rest and move upon. And that's, again, raises this sort of need to have that surface be sort of come to the object and be at an ideal location in order for these motion primitives to work. Not necessarily for grasping to work, for these motion primitives to work. Another thing which I'm only just going to mention because it's ongoing work is now how are these digits arranged? The manipulator on the left, you can see, is in this what we call this four-finger cross, versus on the right is this more anthropomorphic design. And there's been a number of explorations of this, for example, in the Aaron Dollar and Rob Howe's work, looking into some of these digits need to be on active degree of freedoms to be able to move the configuration of the hand in real time to be able to grasp different objects. And we're seeing something similar with these soft end effectors, whereas the sort of four-finger cross anecdotally can do well with low aspect ratio spherical kind of objects versus more anthropomorphic things which can do far better for in-hand manipulation and stable grasp in general with high aspect ratio objects, cylinders and the like. So more on that in the future. I want to mention a couple other topics. One is that was just talking about the design of the hands themselves, the digits themselves, but we can also do things in a modular sense with thinking about the surfaces. And so Kate Becker and crew, they looked at this a few years ago, where they developed took these sort of soft end effectors, and these are similar to the ones I was showing you for underwater manipulation, and now putting this is a taffeta sheet on the inner surface of the digits, where you can see some of these holes, and underneath these holes is a PDMS membrane, silicone rubber membrane, that when inflated will then sort of push through the inextensible taffeta membrane and extrude into this out of the surface and into whatever the object is that you're grasping. And so what they showed is that they can increase friction in this way by a factor of about an order of magnitude, which is pretty remarkable. And then they had a number of nice demonstrations. How many robots does it take to screw in a light bulb? Where they, in this case, you can just see this object being rotated. Now the actuators are not changing, so there's no inflation or deflation. It's just the surfaces the surface friction is being sort of turned on or off, and then showing that I can then control surface tractions by virtue of the modulation of friction and screw in a light bulb. Okay, so that's another potentially useful avenue. Coming back to this architecture, just again to give another plug for this. SOMO architecture, we can get various, I mentioned this already, but this is based on Pi bullets. This is, Moritz has the goal to try to get to something like a URDF, but with these soft Python, with these Python-based soft simulation tools, where I can then sort of specify in sort of human, readable language what the configuration of a soft or a continuum manipulator is, implement it in this environment, and press go. And he wants to use these things for example, both design for things like how do I then understand a design with respect to various performance metrics, where do I put sensors, but also then things like planning. How do I plan to dunk this basketball with a continuum manipulator in things that would be really difficult to do, of course, with just by sort of hand and pencil and paper. And then the last thing I'll talk about on this specific subject is, well, I didn't mention how we're actually building these things. And one key enabler of all of this is the tremendous efforts that Michael Bell and Kate Becker and a number of other people at Clark and a number of other people at our lab have innovated on, and with collaborations that go beyond our group, of course, from discussions with Oliver Brock's group and a number of our collaborators at CMU and Carmel Majidi's group and a host of others that I'm not giving justice to. But nonetheless, we built up this suite of capabilities in lab for injection molding soft materials, elastomeric materials. And there's a video I didn't play here because it's too long, but Michael's put together also instructional videos, and this is also some tutorial papers that's under review. But basically, how do we create these structures, create them quickly, resolve features that are very, very small, use 3D printed molds and not have to go to the expense of spending thousands of dollars for metal machine molds. How do we insert various things within here? How can we create these complex internal geometries, in this case by using soft cores that are themselves elastomeric that we can sort of pull out after the cure is done? And I'm not doing this justice, but there's a whole suite of capabilities that are now in place. And so if you're interested in getting involved with this kind of research, actually it's fairly low-hanging fruit. It's not very expensive. For a few $1,000s, as long as you have access to a 3D printer, for a few $1,000 you can get up and running and start to build these things. And you can turn around these kinds of devices in a matter of a day or perhaps even less. So that's where we are in terms of thinking about, again, this merger. I'm not going to suggest that soft end effectors are going to take over entirely and do things that rigid end effectors cannot do. No, what I'm advocating for is a merger, is the strategic use of compliance within the end effector, and again, for several goals. One is, how can we just take advantage of the compliance of these materials such that we don't do damage to objects, or that we can be tolerant to errors. So that's one obvious thing. But this brings up questions. Well, all right, how do we get dexterity back? Perhaps if we've lost it through just the fact that we're so backdrivable now that gravity will deform us. And then how do we, along similar lines, how we can incorporate strength back into these things. In particular, strength relative and payload relative to the things that we want to carry, but also our own sort of self-weight. So that's where we are. That's where we're going. I wanted to mention a couple of other projects which are somewhat related and sort of pointing towards the directions we want to go in the future. And this is just a laundry list of things that if I were to be asked, what do I want what do we need to focus on for soft robots? And perhaps these are things that we take it for granted in more traditional systems. Artificial muscles is, to me, the holy grail of robotics, if not of all engineering. How can we create things like muscle and have this be electrically activated? And so I'll come back to that in a minute. Skin-like sensors. I mentioned at the start some brilliant work that's being done elsewhere for sensors which are compatible with some of the architectures that I was mentioning. And I'll go over a couple of alternatives or complementary sensing technologies. I'm not going to talk about energy storage controllers or manufacturing strategies. We've sort of have a stable manufacturing strategy. That's not a problem. Depending upon what type of actuator you're talking about, energy storage is either straightforward or extremely difficult if we're talking about small scales or the need for be compliant. And controllers is also something we're working on by virtue of some of these simulation environments tied to our experiments. But I want to just talk about one focus that we've had over the past few years is these soft actuators that I've been showing you. These fluidic soft actuators are fantastic, and in particular, if you are tethered or sort of have a local fluidic power source, then they're wonderful. Then you can get extremely high energy densities and bandwidths that are useful for the types of things that we want to do. But if I need to have something electrically driven for whatever reason, there might be a number of good reasons. Then what do I do? And so the most promising technology in my mind are dielectrical elastomers. but they've been hampered historically by a number of challenges. So that natively their energy densities, and this has been shown, I don't know, 20 years ago now, or more than 20 years ago now, natively some of these silicone-based or acrylic-based elastomers can achieve extremely high energy densities, but in the past they require materials which would be strain stiffening such that they don't undergo this sort of pull-in instability upon high applied fields. And so people to get over this have used pre-stretch. So basically stretch the materials, then attach them to typically a rigid frame, and that sort of starts to cut at the benefits that you're getting out of these soft materials by having some of these rigid materials in there. So that's one. The second is that if these materials can undergo dramatic deformations, tens to perhaps even 100% strain, how can we get highly conductive electrodes that are compatible with those sorts of strains? And in particular, we want things that are solid state. So it'd be nice to get away from liquids and greases or suspensions of conductive particles in greases, just for obvious reasons. And then lastly is they're relatively high fields, tens or more of megavolts per meter of types of fields that we want to use to drive these things. So that's not going to change necessarily unless we come up with some dramatically different dielectric materials. But we can think about the processing to get the layers thinner and thinner and thinner, such that we can get down to reasonably, on the order of, let's say, hundreds of volts, ideally perhaps, but even down to a couple kilovolts would be good. So this is an example of work by a number of people. Mishu Dududa, who's now at the University of Toronto, and he created these processes where he could make there's over 1,000 layers in here. We create these multi-layer devices. Which are separated by stamped carbon nanotube electrodes that are tens or hundreds of nanometers thick. And so having these sort of solid state, highly conductive nanotube electrodes, very thin such that they don't affect the overall compliance of this system, and the processing steps that he did allowed him to make many layers of these things such that we could actually create sort of more macroscopic motions that sort of look muscle-like and indeed rival some of the qualities of skeletal muscle in terms of energy density. You can get almost 20 joules per kilogram of energy density. Bandwidths on the order of 10 hertz or so. With these materials, hundreds of hertz, as Kevin Chen and Xi Zhu and others have shown. Kevin's now at MIT, who have shown with silicone-based elastomers. But nonetheless, we can start to think about muscle-like properties here. So I'll stop with that. And then sensing is another obviously really important thing for us to think about. And for a while, we've done things with liquid-based sensors, so liquid elastomer composites, and these are things that have been typically motivated by human-centric wearable applications. Where this was originally Yonglei Park, who was with us a number of years ago, and Rebecca Kramer and Carmel Majidi and Yit Mengush and a number of other collaborators that we've worked with on this. And this is sort of an exemplary device which is based upon an elastomeric material with microchannels that are based upon how those microchannels are arranged and then filled with a conductive liquid. We can read out directional strains and normal pressures, and this is a very mature technology now that, as I showed you in the previous slide, has been applied to a number of wearable devices for hands and fingers and shoulders, with David Newman's group on one of their NASA projects, and lower limb things for monitoring gaits with Connor Walsh and all over. More recently, I wanted to plug a technology by Xi'an Araromi, who developed this sensing technology called SCARS. And that's an acronym which I'm not recalling off the top of my head, but the premise is straightforward. The implementation is rather nice, but the premise is straightforward. I've got this sort of serpentine conductive channel, and this is a conductive composite material, whereas the material itself is conductive. But if I start to compress it, then I get an increased conductivity just by the fact that I'm sort of making the physical contacts between these serpentines. And if I stretch it, I lose that. And so I can read out that stretch then as a change in the overall resistance of this structure, and I sandwich this between various layers of materials. And Sean and this is Moritz now being the test subject here, through a classification algorithm of gestures, can then wear this. So these sensors are embedded within a sleeve, and you can kind of see where they are. And what they're doing is just measuring very, very subtle motions of Moritz's underlying musculature in his forearm. So when he moves his hands, certain muscle groups change their, they move. And this is being read out just due to the extremely high gauge factors we can get out of these sensors. And then the little dots that he's wearing here is just for sake of motion capture external, that gives us ground truth measurements. And we can do both continuous and discrete gesture recognition. So I'm out of time, so I'm going to stop, but I'll just rifle through a couple of other things that we're doing that don't necessarily have to do with soft manipulation. A couple of years ago, we worked with Jennifer Lewis's group to create the Octobot, which was, we hyped it as the sort of first entirely soft robot. This is driven by chemical fuel, chemical decomposition, monopropellant decomposition process, and a microfluidic oscillator structure that sort of flaps these soft limbs, and we called that a robot, but nonetheless it's the embodiment of a number of technologies that we're very excited about. We also work not just in sort of rigid materials and rigid laminated structures, but also this is work by Tommaso Renzani and Sheila Russo, who are now at BU, on multi-layered laminated devices that operate by fluidically actuating various internal microchannels, and we can get very complex structures, motions, three-dimensional architectures, and then if you pump in uncured materials and then cure them, then you can get sort of static structures for a sort of self-assembly process at small scales. We're working, this is Vanessa Sanchez's work, working with a number of groups locally here to try to take some of the concepts that we were talking about with respect to sensors and actuators, and now having a more of a sort of tight marriage with textiles and sort of getting these things closer to wearable robots. And she's doing wonderful work now, thinking all the way down at the fiber level, textile level, and all the way up to the sort of robot level. Totally changing subject here. We have, similar to RoboBees, we make these things that are little legged devices that are now fully autonomous and can do all sorts of interesting little dances. Because gravity matters less at these small scales, these things can also, climb on walls and ceilings. This is supposed to be showing that it's upside down. It's hanging upside down and can walk inverted and vertical locomotion based upon electroadhesion. That was a demonstration a couple of years ago. We're part of, I'll plug a couple of projects and I'll stop. The first is we're part of this RETHI program that's a NASA project led by collaborators at Purdue, and this is where we're trying to now think about soft actuators. This is the topics here. Soft actuators, soft manipulators to assist in sort of co-robot applications on Moon, on lunar or in Mars environments. And then the last thing I'll pitch, which is going to sound kind of crazy, is that we're part of this now project that just started called Project SETI, the Cetacean Translation Initiative, which is a group, it's a large team, it's a group of roboticists in my case, and we're working with the great Daniela Roos on this, as well as a number of marine biologists, machine learning experts, linguists, to try to gather as much data as we can about whale speech, decode that using some classification algorithms and find structure in this, and then perhaps talk back. So I'll stop. I'll say again, thank you so much for the invitation. I'm sorry I went a little long here. I can't thank my collaborators and colleagues enough, and I'm sorry if I left anybody out here, and our sponsors, and maybe years from now I'll see you again.
Okay, thank you, Rob. As usual, well done. Fantastic talk. Thank you. We have quite a few questions. We have a few more minutes left. So maybe I will repeat the QA questions in the box. So Rob, the first question is, where does the real-time computation happen in these demos? Specialized hardware on robots or offline CPU? Do you see any compute bottleneck or challenges in these systems?
Yeah, it's a good question. This is all of this is off board, and it's relatively simple. It's basically just it's just actuation sequences at this moment. When it gets a little bit more complicated would be if we're starting to think about integrating some of the sensor information for local or global feedback. Not something that we've done yet, but in other systems like in RoboBees and other sort of complex dynamical systems that also perhaps have some interesting dynamics. We've also done this with just real-time control systems, either embedded in microcontrollers for simple models or in MATLAB Simulink real-time operating systems. But for now, for the soft manipulation stuff you saw, it was all just sort of pre-programmed sequences. The thing that we're trying to get to would be taking some of these more complicated systems and complicated interactions, implementing this in the simulation environment that I was mentioning, learning policies that would be then, for example, just training networks, and then having those networks can then be presumably rather simple, or at least, order, a few layer sort of networks that then could be implemented on a microcontroller embedded within the system. So we're trying, we're open to all approaches, but everything in terms of manipulation you saw was pre-programmed.
Thank you, Rob. I will repeat questions from the QA box because please note there are a few thousands of people on the Bilibili live broadcast platform. It's interesting many choose to join from there instead of Zoom. So we encourage you to continue to watch the Bilibili live broadcast. So next question, Rob, do you see any potential for the use of data-driven models to improve the performance of motion planning and control of a hard-to-model soft or hybrid robots and grippers?
Yeah, that's a great question too. I mean, I think first of all, one of the things I wanted to get through is that we're fairly agnostic to soft or hard or some merger of the two. I think at the end of the day, in terms of the hardware designs, the best designs I suspect will be some combination of strategic compliance and strategic rigidity, depending upon the task and the objects. And so in terms of data-driven, absolutely, yes. In terms of data-driven, I mean, both sort of experimental data-driven, if we can sort of produce design variations quick enough and evaluate them, which is where we've put a lot of our emphasis to date, is just building up infrastructure to do that. But also in terms of some of these more simulation-based approaches, again, I didn't really get too much into this because it's something that's sort of, it's in review and forthcoming, but this physical environment, or the simulation environment that we have, is calibrated based upon some simple experiments that you run to inform then material properties that are implemented and simulated in that environment. So we are sort of very much doing data-driven, model experimenting, stepping back and forth between simulations. I wish I could tell you that it was methodical, but we're basically just want to throw everything in the kitchen sink that we have to answer some of these questions on design and control.
Rob, very quickly, last question about hydraulic and pneumatic actuation, because you showed mostly it's air pressure powered. The question is whether hydraulic can help achieve higher bandwidth. Go ahead.
Perhaps higher bandwidth, yes. It's a bit of a trade-off there, of course, because then you have greater self-weight, and actually if the weight of I don't remember the volumes off the top of my head, but presumably whatever fluid that you're putting in, the working fluid, if it's a liquid, then it's going to be roughly comparable in density to the elastomers that we're using. So it would probably be a insignificant increase in the effective inertia of these things. But yes, in terms of the actual actuation speeds, sure. We tend to just choose the working fluid based on the environment, really, and it's, for in air, we use air, for in water, we use water, just so we don't have to do any sort of compensation or worry about failure.
The time is up. I see many fantastic talk. Congratulations to Rob. And Rob, as usual, it's a wonderful talk. And I'll move on to the next exciting plenary panel led by Ken. And I thank you on behalf of the whole community. There are thousands of people listening to you, and I thank you for your great talk, and it's great seeing you, Rob.
Thank you for the invitation. Thank you so much. And I really look forward to the next conference when we're all together.
Thank you. Thank you.